animations of 3D manipulators. Okay, so here's a recap, which is when we talked about 2D manipulators, we looked at this command called line, and we saw that if you want to draw a line from the point x0, x1 to y0, y1, just put it this way, x0, y0 is one point, x1, y1 is the other point. If you want to connect these two with, say, a red line, then the command is line, give the x coordinates of the 2 points, give the y coordinates of the 2 points, then you can say color, then you can say red, and then there are other options such as the line width and so on. So that will draw the line in 2 dimension. Okay. Now, if you want to do the same thing in 3 dimension, then the same command holds true, except that now you will have a third dimension, x0, y0, z0, x1, y1, z1. And let's say we want to draw that in green. So all you'll do is add that third coordinate to the line command. So line x0, x1, y0, y1, z0, z1, and then color green. And then you'll have a line in 3 dimensions, which is of green color. So that's the key behind doing 3D animations. There's nothing much to it. Now, how do we actually translate this to 3D manipulators we talked about? So we looked at the manipulator with, and I'll just draw generic manipulators. Something like this. Somewhere the link, this one is the ith link, and then it keeps going on till the end effector. So this is the nth link. This is the ith link. And then the brace frame is obviously here, x0, y0, z0. And then this one has the ith frame, xi, yi, zi, and then same for nth. Now what we've done is we know there's a transformation hi2. Sorry, it's hi minus 1 to I. So this is giving how the I minus 1 ith link is related to the I minus 1 link. And so there was this formula which I wrote down from the DH convention. Okay, so if you want to find the nth link, the position of the nth link, what you do is you find hn. Hold on, I think I'm doing an error in my convention. Yeah, this is not right. This should be I minus 1. So yeah, so it's the ith link to the I minus 1 link, where I minus 1 is before ith link. Okay, so hn0 is h10, h21, so on till hn minus 1, right? And that formula is essentially rn0, 0, tn0, 1. Okay, and in dn0 are the x coordinates, y coordinates, and the z coordinate of the end link. Okay, so that's the position of the nth link. That's all we need for the end effector position. Now, if you want to use this information to get the coordinates of each link, end of each link, right? If you draw the end of, if you know the end of each link, then all you need to draw is a line connecting the two. So that formula is actually sort of buried inside the formula I just wrote down. In fact, you can write hi to the frame 0 is h10, h21, hi, I minus 1, and that will simply be some rotation matrix. Okay, there is be a position matrix or a position vector, and this basically gives you the position of the ith link or the end of the ith link or the ith reference frame. So xi, yi, zi. Okay, so in order to plot, all you need to do is you need to go for from I equals 0, 1, 2, all the way to n. And so what you'll get is if you put d1 0, you'll get x1, y1, z1, and of course d00 is 0. So let me just write that down first. So d00 is x0, y0, z0, which is normally the origin, right? So we don't really have too much there. But d10 is x1, y1, z1, and d20 is x2, y2, z2, and then we can keep doing that till dn0 equals xn, yn, zn. So all I need to do now is take this information and parse it in the line command, and I say x I minus 1 xi, yi minus 1 yi for the y coordinate, and then zi minus 1 zi for the z coordinate. And then if you want, you can put color and so on. But essentially, all the information you need is buried inside the D matrix or the D vector, and the D vector is in turn buried inside the H or the homogeneous matrix transformation from I to 0. So once we compute the H's, which in turn come from the formula which I wrote for DH, which is I minus 1. So once we have these formulas, we can then find HI with respect to frame 0. And then once we have that, we just pluck out the third column to get the positions of the end effector. So I'm going to show you how to do this in MATLAB now. I'm going to show you a visualization of the two of the three manipulators we talked in this class. So first one was a two-link manipulator, planar manipulator, and the second one was a three-joint manipulator, but in 3 dimensions. So I'll go to the code and switch my computers. Run this code. And once I run this code, this is what I see. So this is basically showing a two-link manipulator. X is, note, it's in this direction, Y is upwards. Here what I did was I essentially specified the H homogeneous transformation related to the DH, and that was actually in this file, which basically computes the H by taking this 4 homogeneous transformation involving 2 rotations about theta and alpha, and then there is a translation D and A, right? So this is the formula, and I just write it once, and I can just call it to get the H value. Next, what I do is I specify the first line of that two-link manipulator, which was basically a planar manipulator. I get the HO1, okay? Next, I supply the second line of the DH, and I get, hold on, this is not right. This is the code, my bad. This is the two-link, that was actually the 3-link. So I get put the first line, put the second line, and once I put the first and second line, I can then find the end of link 1, which is basically the 4th column, right? What is H01? It is R01, D01, and then there is 0 and 1. So this thing here is basically is equal to D01. Essentially, that I'm getting the first 3 elements of the 4th column. Okay, and then I get H02, which is H01 times H12, and then to get the end of link 2, all I need to do is get D02, which is going to be R02, D02, and I get this part, which is the first 3 rows, sorry, the 3 rows in the 4th column. Okay? And then I have the position end effector, which is the end of H02 or the or this D0 to the X, Y, and Z. In this case, I'm only interested in the X and Y because this is a planar manipulator. So then I just need to use line, connect the first 2 points together. So link the origin with end of link 1. Okay, so that is, you see the figure. So line 32 basically joins this point to that point. Okay, then I have line 36, which is connects link 1 to link 2. So that is this point for end of link 1, and I need to connect to end of link 2, and that's here. And so then I do the XYZ, and then if you want to have a particular view, I don't see where I do that. In this case, I just, yeah, it's a planar plot, so it's not a problem to, it just shows the top view. So that is how to do animations of 3D manipulators in MATLAB. Now, this one is a different problem. This one is a 3-link, and I think I have it here. Should be, let me pull it up. So here's another manipulator. This has 1 revolute joint and 2 prismatic joints. Okay, and I've not really drawn the links here. I just showed the joints. As we said, we don't need the links to do the DH table. So here, what I need to do is next do the same thing, which is pull out each line in this DH table, then get the corresponding H matrices. Then end of link 1 is the 4th column of H01. Then I have the 4th column of H02, which is formed by multiplying H01, H12, and then same for 3. So finally, I join the origin with the end of link 1, same for link 1 and link 2. So link 1 is here, link 2 is there. These are the X, Y, Z coordinates, and same for the last link. So when I run this, this is what I get. It's okay. So this is how the manipulator looks if you do a plot and you connect the links together. Okay, and then you can change the position orientation. So in this case, let's see, I need to change this. If you remember, it was theta 1 was one of the parameters, D2 was the second, third one. So let's just change this to 0.4. And if you want, change it to pi by 2, and then run this. And then what you see is, doesn't change much. Here it is. This link got lengthened, but that one changed much. It's interesting. Let me just change it to 0 and see what you get. Yeah, it doesn't quite change. It actually rotated the manipulator. So now the blue link, light blue link, is actually pointing away. It's along the Y direction. Earlier it was along the X direction. Okay, so that's how you do plotting. It's really simple. It's just an extension of the 2D text of 3D manipulators. Okay, so what is this? Well, if you have a manipulator with links like so, and this is in 3D, but I'm just showing it in 2D. This is the end effector, and this end effector could be a gripper like this. And this gripper has to essentially grasp an object, right? Okay, so if the gripper has to grasp the object, you need to ensure that the gripper is positioned near the object. So it needs to have, we need to define an X ref, Y ref, and Z ref. So that will just ensure that this gripper is in the vicinity or close to this object. That's the first thing. The second thing is you can see that the gripper has this, the direction in which the gripper can grip the object depends on how the gripper is made. Like in this case, the gripper has to come something like this in order to grasp the object. So then what we need to ensure is that the gripper is oriented in the right direction, else it will not be able to grip the object. So in this case, we want to ensure that the rotations, which is in our case, we parameterize rotations with the 3 to 1 Euler angles, should be satisfied. So we have theta, the phi, ref, theta, ref, and psi ref. Okay, these should also be satisfied. So what we need to ensure is that 6 numbers, this is for the end effector. So we need to ensure that the end effector is situated such that it satisfies all these reference positions which you would specify because you know where this object is, right? So given x ref, y ref, z ref, phi ref, theta ref, psi ref, find um, the joint angles. Okay, so this is it. Now, clearly, if you have a 6-dimensional, well, you have 6 things you need to satisfy, then in order to do so, you need to have at least 6 links, right? You need to have 6 degrees of freedom. So you cannot get a general purpose manipulation unless you have at least a 6-degree of freedom robot. So you need at least, so needs at least a 6-degree of freedom robot. So when you look at the catalog for manipulators, you will see that most of the manipulators are actually 6 degrees of freedom. Some of them are actually 7 degrees of freedom, which means it gives you more flexibility in terms of what you can do. But most of the time, 6 degrees is adequate. Okay. So now the question is, how do you get the end effector to position itself at that particular location? Now we've seen that the position orientation of the end effector is given by this particular homogeneous transformation from frame n to 0. Okay, so inside dn0 is buried the x, y, and z positions of the end effector. And so what you need to do is you need to ensure that x is x ref, y is y ref, and z is z ref in order for the manipulator to be located at the object position. However, it's less clear what you're going to do with the Rn because there are 9 numbers, right? 9 numbers. But these should match the theta, phi, and psi. Okay, in fact, they should match theta, phi, and psi ref. Okay, so given 9 numbers, how do you make them equal to these 3 numbers? In a way, there is a transformation which gives you that, right? So what we'll do is essentially look at what we get when we multiply those 3 rotations together and relate it with Rn0 in order to get what these phi, theta, and psi are. So what I'm going to show you is, well, let me just pull this from my notes earlier. So this is a formula I wrote down sometime back when we talked about 3D dynamics. So given the 3, 2, 1 sequence of rotations, you can write the rotation formula by taking rotations about z, y, and then x, and then the formula comes out to this. And now you can see that if you want to find theta, it's simply here. So what you do is you say minus sine theta. So what we'll do is we try to equate this with Rn0. So Rn0 would have, let's say R11, R12, R13, R21, R22, R23, and R31, R32, R33. This is what comes when you do the computation by putting in the values for the different DH parameters as well as the free parameters, which will be the degrees of freedom. So what you need to do now to find theta is you only need to say minus sine theta is R31. And from that, we can see that theta is sine inverse of minus R31. So that will give you theta. Okay. So once you found theta, what you can do next is you can use the third row, second column to get the value for phi. So we can see that cosine theta sine phi equals R32, right? R32 is this. However, we know what theta is. It's basically sine inverse of minus R31. So you will have a numeric value for theta. All you need to do now is put that in here. So you'll get a numeric value for cosine theta. And then all you need to do is invert phi. So we'll get R32 divided by cosine theta. And then we need to do the sine inverse. This is just dividing throughout by cosine theta and then inverting sine. So that's the formula for phi. And then finally, to get psi, we can observe this part. And we can see that once we know theta, psi is easily found. So then we'll write cosine theta cosine psi equals, cosine theta sine of psi equals the second row first element, so R21. And so sine of psi is equal to R21 divided by cosine theta, because we know the numeric value of cosine theta because we know theta. And then I need to do sine inverse. Okay, so this is how you get theta, phi, and psi. And once you have that, doing the inverse kinematics is trying to match this theta, this phi, this psi, and then the x, y, z I got from the D. Okay, and so next I'm going to show you code which does. But before, this is the motivation for doing the inverse kinematics. This is a manipulator which is well known as the Stanford Manipulator. Okay, so the DH table for this is going to have 6 rows because there are 6 links. I also drew them here. If you want to go back, in fact, one of the exercises you can do is, given the DH table, can you draw this? So far, we've only done this way. Given the links, we are trying to find the DH table, right? But you need to know the other way too, because when you get the manuals for these robots, you'll generally be given the DH parameters, and sometimes you're not given this pictorial representation I've shown on the left. Okay, so this is the Stanford Manipulator, and our goal is to, one, find the position and orientation of the end effector, which we've seen in the past. It's just a matter of plugging in these table in the H matrices to get it, and then do a forward and kinematics and animation, which we've also seen. We only need to get the 4th column in order to get the ends of each link, which can then be joined using the line command. And then finally, the last step is to the inverse kinematics. So I will give you the end effector position I desire, and then you will find the angles, theta in this case, and I think one of them is D, such that the manipulator extends itself to that particular kinematic position. So inverse kinematics. So for that, we are given xref yref, zref, theta ref, phi ref, psi ref. Find the joint angles. Okay, so I'll show how this is done in MATLAB. So there is a main file which basically sets up all these parameters as global variables, and I do that only because it's much easier to exchange data with this end effector position. Okay, this one end effector position is very similar to what we did for 2D manipulators, right? For 2D manipulators, the end effector position essentially supplied the x and y coordinate of the end effector. In this case, this also supplies the x, y, but also the z and the, it supplies the x, y, and z coordinates, right? And it also supplies the phi, theta, and psi. So it's all the 6 numbers for the end effector. And then these dis are basically the reference, whatever you want. So this code is, the end effector is an extended version of the one we saw for 2D link manipulator. The main file essentially takes this DH table and puts it here. And some of these variables are ones we choose, right? The joint angles are something we choose. So the joint angles, the initial guess is right here. So this is one of the initial guess we want to initialize our solver. In this case, we use fsolve to solve for the inverse kinematics, just like we used fsolve for the 2D manipulator. So then we have the locations of the end effector. So I give you this where I want the end effector to be, so it can grip some object. And then there is the TH table. And then finally we solve using fsolve. So let's see what this does. So the output is here. Okay, it doesn't quite look like the figure I showed you because it's there are cylinders and so on. But this is just showing a sketch of what the manipulator should do when you specify a certain end effector position. We can change the end effector position to whatever you want. Let's try 0.5 and see if it gives an answer. Sometimes you may not get an answer because you're away from the manipulator limit. So here is what you get for a different reference position. The f-val tells you how close is the end effector to the actual reference position or desired position. So here it's saying it's up to 1e-8 or 10 raised to negative, which means it's very accurate. This is the solution for the 6 values for the joints. And then if the thing converges, then it will give you an exit flag of 1. So where that comes in, it comes right here. There are 3 outputs: the solution, the value, how close it is, and then exit flag tells you if it's successful or not. Okay, so any questions on this? Okay, so you have a homework question where you will do this for UR5, which is a very popular manipulator out there.